Over the last 12 days, the sky above Hyderabad has looked exactly like this. A thick ceiling of ominous dark clouds rolling over the city, suggesting a massive downpour is imminent. Yet the pavement below remains bone dry. We are naturally wired to read the sky simply. Dark clouds mean heavy rain is on the way. But to a climatologist, that darkness represents something else entirely. It indicates a high optical depth. There is an immense volume of water vapor suspended up there, thick enough to block the sunlight, but it is trapped. Having all that moisture overhead doesn't guarantee a single drop of precipitation. The atmospheric physics required to squeeze that water out of the sky are currently broken, locking the region in a monsoonal gridlock. Hyderabad sits on the Deccan Plateau, well within a rain shadow region flanked by the Western Ghats. This specific geography makes the local atmosphere highly susceptible to microphysical bottlenecks. To figure out why the rain won't fall, climatologists have to perform an atmospheric postmortem. We systematically dissect the vertical column of air above the city, starting from street level and moving all the way up to 5,000 meters. Local meteorological institutions constantly monitor these stagnant cloud systems using Doppler weather radar, searching for exactly where the precipitation cycle is failing. By diagnosing the exact failure points within this vertical column, engineers can formulate a precise chemical intervention to force the system to yield. This diagram of the atmospheric column shows where our first major bottleneck occurs, deep inside the dark cloud mass itself. Hyderabad is a sprawling urban center. High concentrations of anthropogenic aerosols, vehicular emissions, industrial sulfates, and ordinary dust are constantly rising from the ground and diffusing directly into that cloud layer. Inside the cloud, these pollutant particles act as cloud condensation nuclei. Instead of the available moisture collecting on a few particles to make heavy raindrops, the water vapor is forced to distribute itself across billions of tiny individual dust particles. This is called the Twomey effect. This data visualization tracks the resulting droplet growth. Because the moisture is stretched so thin, the droplets hit a hard limit. Their average radius stays permanently locked below 20 micrometers. At that microscopic size, the droplets are incredibly uniform and ultra-light. They lack the mass required to generate terminal velocity, meaning they cannot collide, merge, or fall. This aerosol overload creates colloidal stability. The moisture is locked into place, suspended indefinitely as a sterile, dark blanket over the city. Next, we look at the boundary layer. This diagram shows the gap of air between the city ground and 1,500 meters up, directly below the cloud base. Even when rain does manage to form, a wedge of dry, continental air frequently slips into this lower boundary layer. As raindrops fall into it, the dry air instantly dissolves them. This thermodynamic barrier completely evaporates the raindrops midair. It is called the Virga phenomenon, and it explains why you have heavy humidity aloft, but a bone-dry surface below. The third and final bottleneck happens at the very top of the atmospheric column, far above the cloud layer. During a break monsoon phase, a layer of warm, dry air sinks from higher altitudes. This is a subsidence inversion, and it acts as a physical lid pressing down directly on top of the clouds. This thermal lid chokes off vertical updrafts, keeping them well below 2 to 3 meters per second. Without that vertical energy, the clouds cannot build into the towering cumulonimbus structures required to trigger heavy storms. The gridlock is now fully mapped. Hyderabad's moisture is paralyzed from within by aerosol pollution, evaporated from below by a dry air wedge, and squashed from above by a thermal lid. Shattering this gridlock requires an engineering workaround. The first step is analyzing the temperature at the base of the clouds. This diagram shows the 0-degree freezing line sitting above 5,000 meters in July. Our target monsoonal clouds are positioned far below that mark, classifying them firmly as warm clouds. Traditional cold cloud seeding uses silver iodide to freeze moisture, which is entirely useless here. Climatologists must use a chemical catalyst specifically designed for warm cloud seeding. The required payload relies on giant hygroscopic particles. specifically a highly water-absorbent blend of finely milled sodium chloride and a small percentage of calcium chloride. The engineering tolerance for this compound is razor thin. The particles must be milled strictly between 1 and 10 microns in size. If the milling is incorrect, the operation fails. Particles smaller than 1 micron simply add to the urban smog, and particles larger than 10 microns are too heavy and will fall out of the sky before they interact with the moisture. When the correctly sized particles are dispersed inside the cloud, they greedily absorb the surrounding water vapor. They rapidly balloon into giant droplets, swelling well past 30 micrometers in size. These artificially bloated droplets suddenly gain enough mass to achieve terminal velocity. Plunging downward through the dark cloud, they physically sweep up and absorb millions of trapped, stagnant microdroplets in their path, setting off a self-sustaining Langmuir chain reaction. This precise chemical injection physically disrupts the colloidal stability, transforming a sterile vapor blanket into an active rainmaker. Transitioning from microchemistry to the field requires highly targeted, scientifically validated aviation logistics. Before any aircraft takes off, ground meteorologists use Doppler weather radar and Titan tracking software to analyze the internal matrix of the cloud. This table highlights the strict diagnostic thresholds that must be met. Seeding is only authorized when the radar reflectivity exceeds 30 decibels and the relative humidity inside the cloud core is over 80%. Once the cloud is verified, the tactical flight path is mapped. In July, Hyderabad's monsoonal winds push predominantly from the southwest. If an aircraft drops the payload directly over the city center, the time it takes for the rain to form and fall means the precipitation zone will be pushed far east by the wind, completely missing the critical catchments. To account for this drift, the aircraft must fly 10 to 15 kilometers upwind, targeting outer regions like Vikarabad. The pilot then executes a base injection profile. Flying strictly beneath the cloud base, the crew ignites the flares. Natural atmospheric updrafts suck the freshly generated salt nuclei straight upward into the dark core of the cloud. Bypassing the optical depth paradox requires chemical precision, radar verification, and calculated upwind delivery to ensure the payload hits its exact mark. The structural changes inside the cloud happen fast. A successful base injection yields measurable physical results in just 30 to 45 minutes. This simulated radar shows the immediate shift. Reflectivity spikes from weak green patches at 20 decibels into a core exceeding 45 decibels. The newly engineered raindrops gather immense physical mass, punching through the dry boundary layer that caused the virga, crashing straight to the surface. This engineered cascade decisively overwhelms the atmospheric bottlenecks. The 12-day dry spell breaks, unlocking the massive volume of moisture trapped aloft. The physical outcome is widespread, heavy monsoonal rain, finally pouring over the desired target zones. Thanks to the precise upwind flight path, this precipitation drops directly into the vital catchment reservoirs that sustain the urban population, like Osmansagar. Urban infrastructure is specifically positioned to capture and hold the massive storage capacity unlocked by this localized runoff. The dry pavement is washed away, allowing the engineered rain to secure the water supply and sustain the local ecosystem. By treating the atmosphere as a thermodynamic system that can be precisely diagnosed and engineered, climatologists bypass the monsoon gridlock, mechanically forcing the sky to deliver the water trapped inside it.